Okay. Oh, and I should have shared screen also. One of these days, I'll figure these things out. Yeah, okay. So this is the, actually, I'm just gonna share. Someone's phone is going off. Actually, I'm just gonna share everything. Okay, so like I said, take a look at this, and then I will add the actual problem set to Gradescope also, and I need to post this video also. So I'll do that. I'll try to do that soon. But yeah, the big thing I said about Gradescope itself. Oh yeah, so there's a PDF which has the same information attached. But is that I would ask if you can try to upload a PDF instead of images. It's just nicer for everyone, the graders, to deal with and everything. And most scanning software, your Notes app on your iPhone, if you have an iPhone, I think will scan things to PDF. Okay. Any logistical questions about the assignments or anything? Ooh. We're good. Okay. The other thing, so I put this Mathematica notebook, which I'm going to use. I tried to put it as a file, and then I tried to download it, and it did something weird. So I just changed it to a direct link. I think this will work. I just go through my Google Drive. Probably should be using OneDrive, but whatever. So used to Google Drive. Okay, so where'd that go? Okay, this is a bunch of code, which I will talk about. If you watch the Mathematica video, you'll start to see some of this. But what I want to do today in class is actually start trying to visualize some functions of three variables. We did basic 3D space stuff on Friday, right? Just getting used to sort of living in 3D space. Sounds funny, say it that way, but mathematically living in 3D space. And today I want to start thinking about functions of two variables. So let's see. So maybe I have to continuously think I'm gonna pause the share. How does that work? I pause the share, does that, well, let me just go back to here. Okay, so hopefully if somebody's remote or wants to watch this later there, we'll see this on the board. Okay, so let's talk a little bit just about functions like of this form. Right, so functions of two variables. If I take, like if I draw our axes the way we've been drawing them now, hopefully you're getting used to this idea of drawing X here, Y here, and Z here. Let's think about a specific example. So let's think about something like, well, first, I think I mentioned this example last time, just X squared plus Y squared. This is just it has a nice picture example. What you can start to do is you can start to the very bare bone things you can do, the bare bonesest thing you can do, that doesn't make grammatical sense. The most basic thing you can do is just start plugging in values of X and Y. Just like if you were given some function and you didn't know how to graph it, you could plot points. So you could do something like, all right, if X, I could choose some values of X and Y, and then actually think about what Z is. So if I do 0 and 0, I get 0, which to some extent means something like this point is on the graph, right? If I plug in 0, 0, I get 0. If I plug in 1 and 0, I get 1. So, okay, let's think about that. That's plugging in this point. This is the point 1, 0, but I go up 1. So it's actually like that. If I plug in 0 and 1, maybe I should do plus or minus 1. I get 1. So you'll start to see quickly that this is kind of hard to draw. Like if I go over 1 unit, then I have to go up a unit that way. I saw some of you guys on Friday trying to draw like the negative axis back here and the negative axis here. And so I guess I'm also claiming if I plug in this point, then it goes up 1 unit. Who knows if I'm even being consistent about what 1 unit is. It'd be nice if we had 3D graph paper, but we don't. And then if I plug in this, so there's 4 points. If I plug in like plus or minus 1 and plus or minus 1, I think we just get 2. Is that right? So now you got these points. Let's see if I tried to plug in, and this is going to look very ugly very quickly. Like, what's 2 units up? That's about 1. That's about 2. You know, it's going to be really. It gets hard to picture. It's hard to picture, sort of. You can plot points, but it's hard to picture. So instead, I would say have a computer do it for you. But I mean, we're going to think about why the picture ends up being what it is, because we do want to understand why we get the picture we get. For you. So let me share again. So I have this Mathematica software, but even before that, I was going to say the Google search bar is kind of amazing. If you've ever just tried like plot, I think I typed it in earlier today, so that's why it remembers. Plot z equals x squared plus y squared. This is just Google search bar. It plots functions. It's nice. And so it's giving me this picture. And I guess you can even tell that the red is the x-axis. So can you see that? I don't know if it's down here. It says x negative 10 to 10, y negative 10 to 10, z from negative 63.15 to 189.48. So it's choosing this somehow, but I guess this kind of, you can see that little gray translucent plane. I think it's the XY plane. You can zoom in. There's actually, well, you can play this. It'll like just rotate for you. You can drag, I'm just dragging it around with the mouse. You can zoom in. This is, I think this is camera zoom, meaning it'll just zoom in like this if you want to get like a closer look. And then I think there's also, but I think if you switch to this, it's function zoom. So it's actually zooming in. It's actually narrowing the range of x's and y's it's plotting. Actually, you can do. I can use the wheel on the mouse too, and you know. Oh, that's interesting. Oh, that's actually very interesting. You really can see it's like a bowl there, right? Question. Oh, that's interesting. Oh, you can. Good call. I just want like a corner. Oh, wait, what happened? What? Hello. Whoa. I don't know what I did. You messed up the whole thing, man. Let me just replay. It's kind of amazing though that like, again, the Google search bar will do this because in a lot of ways we're going to see what Mathematica is not going to be that much better. So if I go over to Mathematica, so the first command here, it's plot 3D. So it's plotting the function x squared plus y squared. You'll see certain things in the video when you watch it, like that I posted about all commands in Mathematica have to be capitalized. They have to be within square brackets. So if I want to plot, I'm telling it to plot a function of two variables by saying plot 3D, x squared plus y squared, and then this gives you the x range from -5 to 5. This gives you the y range. Everything in any programming language is like a list, basically. So this is a list, x, the variable x, the rate, then minimum value, the maximum value. And then this is just something about labeling the axes. I think one thing I say in the video also is that you can click on, if you hover over any command, you can click on this little info button and it'll pop up like a, one thing I really like about Mathematica is that it's very well, the documentation is very good. And you can sort of see how any of these commands work. Whoa. You get some crazy, neat examples are always fun. Oh yeah, of course, the branch cuts of inverse trigonometric functions. Who knows, but and then also these are code you can run. Like I could change this to like a 3. The other thing you'll see in the video is that instead of hitting return, you hit shift return to evaluate code. Oh, this little thing means it's trying, it's working. Oh, it's having trouble. There it is. Oh, that's because that's an uglier function. Anyways, so here, if I run this command, we'll see. So this is just going to plot. So this is plotting over the range -5 to 5, -5 to 5. It's plotting all these points. So like for example, the values I plugged in are all there, but notice it tells you the, I think I had the axes. Wait, I can make this bigger. Can't I? Yeah. So x goes from -5 to 5. If I drag the y axis is up there for some reason. Moves around. Y goes from -5 to 5, and then z you can tell goes from 0 to like 50 basically. So here's one picture of this graph. There's a slightly better, there's something called contour plot 3D where you actually specify all 3 variables. And if you want an equality, use double equal sign. And then I'm specifying all the ranges x, y, and z. Oh, hello. This gives more of the classic bowl shape because I just specified the z range I wanted it to show me. This one up here is plotting everything. It's basically plugging in every value from -5 to 5 and -5 to 5 for x and y. So from above, it just looks like a plane because it's plugging in everything. So that's determining the range, the height of the box is determined by the values plugged in. But here I'm sort of fixing the z range to make it look a little nicer. And so you're seeing this. But the point I want to make here is that it's just very nice looking. It is sort of like a 3D version of a parabola, right? It actually has a name. It's called a paraboloid. Go back to the board here. So it's called a paraboloid. But the question a little bit you might want to ask yourself is why does it have the shape that it has? So we get this bowl shape that you saw on the screen. You can try to sort of draw maybe something like this. Oh, that's not bad. If I stole my drawing skills, it's a little lopsided. Drawing skills have faded a little bit. I had a friend who was very into his Blackboard drawing skills, like a professor friend. And like I would teach in the room after him and I'd walk in and he'd be like, look at this picture I drew. He would like come and show me on his phone. He would like take photos of his own drawings. It's a little narcissistic, right? A little bit. He's a good guy. But anyways, so it's something like this. I'm definitely not that good. I guess it would be something like that, the z-axis. So it's some shape like this. Maybe you can see it a little better if you do something like that. But notice on this picture on the screen, you can actually see interesting things like from above. God, am I gonna have to share? Problem is you can't see the screen and the board at the same time. It's like, it doesn't, if you zoom in on the screen, you can see the screen, but so I have to share screen like every time I go back and forth. We'll see, maybe I'll come up with something better. But if you look at this, if you look from above, you see all these circles, right? And if you look from the side, you actually see sort of parabola shapes. And so the question is, if you wanted to ask, like, why does it have the shape that it has, this is going to be a clue. Yeah, this is called a paraboloid. And if you sort of want to ask why, the big idea for us to like actually build surfaces in our brain, in our minds, is to piggyback on. There's so much time. I think I said this already on Friday. We're really not very intelligent as a species, and if we want to do things in 3D, we're going to piggyback on our 2D knowledge as much as possible. So the first thing I'll say is we're going to use what are called cross sections. We're going to set x equal a constant or y equal a constant, or y equals constant, or actually you could say z equals constant, although this is going to have a different name, and see what we get. So these are actually going to be called contour lines, not cross sections, which you'll see why probably pretty quickly. And see what we get. For example, if you just took like, you know, if we have z equals x squared plus y squared, but we set, let's say, let's set x equals 0. So in this picture, x equals 0 is what? What part of the picture? We looked at this on Friday. Yeah? First one. Well, if x is 0, it's the yz plane, right? Yeah, good. So it's the yz plane. So it's like the plane of this blackboard, if x goes that way. Good. So, so that's like the yz plane. So this is basically, if we do this, we're intersecting our surface with the yz plane. And if we do that, we kind of clearly get z equals y squared, right? Just plugging x equals 0 in. And so that is actually a parabola. Forget this being 3 dimensions, just think of the plane of the blackboard being y and z. That really is this parabola right here. Right? This right here is the parabola z equals y squared and x equals 0. If I have to say, I should say x equals 0 to specify. Does that make sense? So that's called a cross section. And then we can, yeah, so that's that specific cross section. And if we just picked a bunch of cross sections, we'll get a bunch of slices. We're basically slicing this object, right? So we're slicing it and we'll get different slices. If I tried, I hope this is, I guess anybody watching this later can rewind the video if they need to see that up there. But if we try something like, you know, we could then start doing this for a bunch of different values of x or a bunch of different values of y and see what we get. So, so other values of x, say, if we did x equals 1, we would get z is 1 plus y squared, or y squared plus 1. If x is 2, we would get y squared plus 4. If x is 3, and actually this could be plus or minus 1, plus or minus 2, plus or minus 3. We get z is y squared plus 9. And you can see it's a parabola that's sort of moving up. If I think about x equals 1, that's sort of say, like this board, this wall right here is x equals 0. If I move out a unit to x equals 1, that's like here, and we get some parabola shape shifted up a little bit. If we go out to 2, it's now shifted up by 4. If we go out to 3, it's now shifted up by 9. And you can sort of start to see how you might get that, right? So these are all parabolas just shifted up by various amounts. And you can also see that in the, so these are the x equals constant cross sections. This is what they're called. And you can see that the y equals constant cross sections are going to be similar, right? There is a symmetry here in x and y. You can sort of switch x and y without changing. You know, you can swap the roles of x and y in this and nothing changes. Are similar. And let me just think about this. So you can see those parabolas actually on this picture, right? Like, I mean, I guess there's more. There's not just the 5. But you can sort of see these parabolas that are getting shifted up in this direction. And if I turn, rotating these things is always dicey. I just turned it 90 degrees. You can also see those parabolas there. Oh, I didn't share screen. Oh my God, I'm gonna have to. Okay, so you can see the parabolas there and there, right? And I even have there's a nice mathematical command that will show this actually. This is a great command called manipulate that basically is gonna plot x squared plus y squared for different values, for different fixed values of y. So here you can see there's a little y is -5 in this case, but I can actually sort of see how it's going here, and I can even play it like a movie. So these are all the different cross sections for different, I guess these are for different values of y. So these are actually the y equals constant cross sections. And you get this movie of this surface by slicing it and like seeing how as you move the slice, as you move the knife that you're slicing with, what the different pictures you get are. And then from there, you can sort of try to rebuild the surface in your head. Like the question is, from that, can you sort of see, oh yeah, the whole thing's gonna be a bowl shape. Some of you are like, yeah, and some of you are like, huh. It's good. It takes some time to get used to, but hopefully you can start to see that. So anyways, this is a very nice command here. Questions about any of that? Literally, I could switch y and x in this command and nothing would really change because the roles of x and y are completely the same. I mean, it's symmetric. This expression is symmetric in x and y. So either way you slice it, you get this sort of shape. And then you can try to picture. I don't know if this is evocative of anything, but I'm trying to say it's a bowl. It's a paraboloid. Okay, so that's interesting. So those are cross sections, and a lot of times just trying to visualize surfaces, we'll look at cross sections. Let's see. Oh, then we can also do the z equals constant cross sections. And if you do that, well, thinking about z equals constant is slicing it horizontally. Oh no, that does suck. Sorry, dude. There's I just go get paper towels from the bathroom. Water spill, no worries. So okay. So we did, so the x equals constant, y equals constant cross sections are these vertical slices sort of parallel to the YZ plane or the XZ plane. So now you could also do these horizontal slices. And we don't tend to use the word cross sections. We tend to use the word, there's different terminology, like there's level curves or contours also, I'll say. So Z equals constant. So these are all the points at the same height. If we pick up a specific Z, right? So for example, Z equals 9 and Z equals x squared plus y squared. That implies x squared plus y squared equals 9, which is a circle of radius 3 centered at the origin. Oh, I did this wrong. Okay. I'm drawing on a blackboard wall. You always draw the circle first and then the axes, or else you get weird lumpy circles. That's actually a little bit lucky. So, okay, so this is a circle of radius 3, right? So all the points at height 9, so all the points at height 9, for example, at height 9 make a circle of radius 3. Okay. It's a whole thing over here. Oh no. more paper towels. Okay, so wait, let me not move this too far. Wait, am I still doing the share? Okay, I just want to show the board for people who are nobody at home, but anybody wants to watch later. Nobody in this class is quarantining for COVID, huh? All right, good for us. Good job, guys. Okay, so does that make sense? And then at different heights, in fact, you can see this. Oh, let me go back to the picture. Here, if I can just pause the share. There's a pause share. I'm just not sure what that does. Okay, so yeah, if I go back to this, I can look at it from above, and you can actually see the Z equals constant cross sections, right? You can see these circles, which are all the points at the same height, right? From there, it's these. You see this, these sort of lines at the same height, and if you look from this way, you actually see the circles. There's actually a different kind of visualization of this function called a contour plot. Well, here, if I just show you, this is more like, this is the contours. This is setting Z equal to different values. Slow it down, I think. So this is setting Z equal to different values and just showing you. Again, it's like an MRI of, I had to have a root canal this summer, and now it's fine. Now they have this thing. I hadn't been to like an endodontist in a while. They have a thing where they like put your head in a thing and they go all around it with cameras, and then it's basically like a full 3D picture and of your tooth, and they have all the slices and the guy, and so the endodontist was showing me, and it was just like, it's exactly like this, basically. It's like, that's the inside of my mouth. No, so it's just like they take all the different slices. So this is basically what an MRI looks like. So that's at different heights, and we just get this sort of expanding circle. There are interesting things even to say here qualitatively, like the circle expands sort of quickly at first and then slows down, right? And that actually is something about it growing fast, and then, well, it's getting higher faster, but it's sort of radius is expanding slower, which you may have to think about it, but I think it does correspond to more of a bowl shape than like a, yeah, so there's this, and then you can actually do what's called a contour plot, which is basically like a topographical map, which just plots a bunch of different contours a bunch of different of these cross sections. And this is actually telling you the height. So I guess it's doing every fifth, every 5, height 5, height 10, 15, 20, and so on, right? So yes. What's the share? Let's see what that does. Recording. So yeah, so back to the board. These are called, there's a couple different names. Level curves, which hopefully is somewhat evocative, all the points at the same level, at the same height, or contours. And so we can also draw what's called a contour map. So instead of a 3D plot, we can actually get sort of a 2D rendering of a 2D representation of a 3D surface by like a topographical map. So the 3D plot, we can draw what's called a contour map or a contour plot. I guess it's called a contour plot, which is like a topographical map. Okay. So that's the idea. That's some idea. So that's really how so when I'm saying we're piggybacking on 2D, we're gonna just use all these slices instead of trying to visualize the function all at once. We can just use all these slices. Okay. So let me just say, okay, so let's look at a different function, because that was a lot on just the same function. So what about x times y? This is already interesting to think about, like what this is gonna look like. Z equals x times y. And you might wanna think about the vertical cross sections, like what do you get, what kind of things do you get if, say, you do y equals constant cross sections? I plug in y equals 3, y equals 4. Yeah. Yeah, straight lines with the slopes changing. So that's interesting. So the slices are like, I guess when y is, or when x is 0, again, if we want to do it this way, it would be what kind of line? Horizontal line. And then as x increased, the slope would increase. So it's something that's like turning that way. Then if we go this way, it's like turning that way. It's a little bit hard to picture what's going to sweep out. But I do think I have a, oh yeah, here's this picture. Here's a picture of this. I guess these are y equals constant cross sections. Interesting. Can you picture the surface? It's hard, right? Yeah, it's a little bit hard. And then you could switch x and y, and it would be very similar, right? The cross sections the other direction would also be lines. I could do the plot 3D, but I think the contour plot 3D is actually going to be more evocative. Does anybody have a general name for the shape of this surface? Anybody picture it? When x and y are both positive, it's going to go up. When x and y are both negative, here we go. Let's go. Job. It's a saddle. It's kind of weird. This is called a saddle shape. You can actually see the lines, right? On there. It's kind of hard to see, but you can sort of see them. And it's kind of amazing that the lines are turning. It's like a cross-section of the line, but it's turning, and somehow it's making something curvy, which isn't obvious at all. Oh, one of my favorite questions that I put on tests sometimes, conceptual question, is true or false? If the X and Y cross sections of a surface are all lines, then that surface must be a plane. Is that true or false? False. There's an example right there. It seems like before you see this example, it seems like it might be true, right? They're all lines in one direction, all lines in another direction. How would you ever do that without it being just like a nice flat plane? But there you go. Let's see, just the plot 3D, I think isn't quite as evocative. Again, it's kind of just looks a little bit, I mean, you can sort of see it, but again, you can see the lines really well in this case. But it's just plotting whatever ranges goes with the input values. Whereas this other command, I controlled the Z range. And so I can make it look a little more like a saddle, right? Okay, so there's that. You can also then do the contours. The contours are interesting. If I set Z equal to different constants, I get X times Y equals constant. What happens? What do you get when you plot X, Y equals constant? What kind of picture do you get in the like XY plane? X, Y equals 1. What is that? Yeah. Yeah, right. If you solve for Y, it's 1 over X, right? So you get the 1 over X function. And actually, if you look at this from the top down, you can sort of see those, right? Let's see, what do I have? I have the Y, I think I need to turn it this way. Yeah, and you can actually see the like Y equals 1 over X type, the hyperbolas they're called, right? In fact, I think this even has a name. It's like a, it's not a hyperboloid. It's like what's a saddle? But it might have a more fancy name as like a hyperbolic paraboloid or something. What's that? Saddle. Saddle's much more evocative. Yes, very good. Yeah, no, totally. But then you can sort of, so actually this would just be different. This is that thing where I'm just going to plot different contours for different Z values. So notice Z is the thing here. This is a drag. I can actually drag this. Ooh, that's fun. Let me slow it down a little bit. What happens there when you get to 0? What is the contour at height 0? What's the level curve? Yeah, Y. If X times Y equals 0, then either X equals 0 or Y equals 0. Yeah, it's good. So if I put in 0 here, I actually get exactly, yeah, so let me write some of this down just to have it. I just was, let me pause the share. Okay, so yeah, and then so this is the kind of game you play. You just sort of, you look at cross sections and you look at the contour map and you try to get a sense of what the surface looks like. You know, I mean, part of this is thinking about before we could just ask computers to do it for us, wherever I wrote that down. Right, like this is a pretty recent thing that we can just ask computers to do 3D plots for us. Like back in my day when I was a kid, I had to use my imagination. We didn't even have any of this. No, okay, well, it's true. We didn't, but I'm not salty about it. But yeah, so just example, Z equals XY. This is called a saddle. The X and Y cross sections are lines of varying slopes, like we said. And right, like e.g., If x equals 2, we get z equals 2y. And then the z equals constant cross sections, which remember we're calling contours or level curves. Slash level. This is just the terminology. We get x, y equals constant, which is the same thing as y equals constant over x. So we get graphs that look like that. And so that's kind of right. And these are like for positive values of z, we'll get one like this. For negative, like we did -1, you get -1 over x, which turns out to be like that. So that's why it sort of goes up in these two directions. The graph goes up in these two directions and down in these two directions. Make sense? Oh, and then like the cool thing was when z equals 0. Yeah, this doesn't work when z is 0. Well, no, it could. Well, you can only divide by x if x is not 0, I guess. So, yeah. This is like say z equals 1 contour. But the z equals 0 contour is xy equals 0, which implies x is 0 or y is 0. And so that actually gives you the contour that looks like that, right? So this is the kind of exploration we're going to be doing for a little while, just trying to get used to these kind of functions. Let's see what else I put here. Oh, here's a full contour plot. Yeah. So this is like the, oh, sharing is paused, zoom share. This is the contour plot of this function, and it's like the vertical view. It's like the top-down view of this, right? Okay. You can do other things, like if you want to just do like a plane, for example. Z is a function of a linear function of x and y. Well, I guess I gave it away, but you can imagine that you're just going to get a plane. It's not that exciting, but but you can sort of say, right, if x is constant or y is constant, you are going to get lines. And if z is constant also, you actually get lines. So here's the contour plot. Oh, this actually, it does shading. I think lower is darker and higher is lighter. Height 15, it's a little pop-up right there. You can actually hover over and see. So planes are nice. I mean, you can just sort of mess with different, you know, I could just make up, you know, you could start playing around with different. Let me just throw in like something. What if we want to do something more complicated? Someone give me a weird function of x and y. Sine of x times y squared, or the y squared outside the sign? Okay, so turns out you have to capitalize everything in Mathematica. Sine of x times y squared. Let's see what we get. I'm doing this from -5 to 5. This may not be the right z range at all. I might have to mess with that a little bit. This means it's working. Woo! Nice one. It's sort of interesting that the x and y are sort of separate. Like, what if I tried moving the y squared inside the sign? I'm going to cut and paste it here. Sine of x times y squared. Okay, now what do I want to change the range to? Yeah, sine can never be bigger than 1 or smaller than -1. What happens here? It's thinking. Tension is palpable. Sometimes it thinks, I don't know if these computers are that fast. Broke it. It's very hard to picture what it's gonna look like. I mean, you can, again, try thinking about X is constant, Y equals constant cross sections. Should have done that up here, actually, while this is thinking, oh, now I got the rainbow circle of doom. Sometimes you end up killing, oh, jeez. That's why I had a bad time. So it's sampling and plugging in points and then making some array. Wow. Maybe I should put this down to like -1 to 1, -1 to 1 instead. Let's see what we get. Oh, that's much more gentle. It gets really upset. It gets really crazy. I guess it's changing faster because you're squaring y, like as x and y get larger. We could do -2 to 2, -2 to 2. Let's see what that does. Yeah, so I guess as you get farther away, then it starts getting, it's a weird surface. I mean, although in one direction, like when y is constant, you should just be getting a sine curve, right? Or maybe a sine that's like you're changing how fast it's going. So when y is constant is like, oh yeah, I guess you can even see that. Do you see that? Like the edge of this traces a sine curve. That's kind of nice. But if I turn it this way, oh, it's different. Well, it's sine of y squared, or sine of a constant times y squared. It's interesting to think about why that's like that. Back up here. Okay, if x is constant, what kind of cross section do you get? Parabolas, right? Because sine x is just some number. Oh yeah, and you can see parabolas that way. But if y is constant, you get sines. So you get sine graphs. So this is the kind of thing we're going to do. Does that make sense? One other type I should tell you about maybe is there are also cases where you just want to have like only one variable or the other. Like what if I just do z equals y squared? What's that going to be? It looks like a 2D graph, except we're in 3D space. Yeah. Like a half pipe, there you go, I like that. So it's a parabola, so no matter what x is, the x equals constant cross sections are all the same. They're all parabolas. So it's like a parabola moving back and forth. So there you go. You get like, yeah, exactly a half pipe. So these are actually called cylinders in the book. Anything where you have just one variable. Because like, if I had, well, this is, well, okay, that's different. But anyways, yeah, I could have like that. You could have z equals x cubed. And that's just an x cubed graph every direction. We could have z equals sine x. So that's just going to be a sine wave, right? In a certain direction, because every y equals constant cross section now. So that's another thing that's worth thinking about. These are called cylinders. And then the thing I was going to say for later is that like, what we're going to look at next or towards the end of this week is functions of 3 variables. Now all of a sudden the graph would be in 4 dimensions, which is a little bit tricky. But you can do the same sort of thing like a contour plot. Like think about one way to visualize functions of 2 variables is to do this contour plot and get some sort of picture of what it looks like. You can also do a contour plot here. So if I change w, so here's like x squared plus y squared plus z squared, equals W, just as an example. Okay, so W, I think, starts at, actually having W start having -5 is silly because x squared plus y squared plus z squared is always positive, right? So now if I was to, so we actually talked a little bit about this. It takes a while to render. But yeah, you get some sort of, yeah, if I play it, it's gonna be kind of a, whoa, what just happened? Oh, I need to, oh, let me make this 25 actually. So here we go. So it's like this. And so now it's like an MRI of a 4-dimensional object, which are 3-dimensional slices. And this is gonna be the best thing we have, is almost like a movie. You can think, if you want to think of the 4th dimension as time, this is like a movie of like this 4-dimensional object. We'll talk more about this. I'm just showing you this very into class, just to sort of think about the analog going from a contour plot of a function of 2 variables to a contour plot of a function of 3 variables in 3 dimensions. Okay, we'll stop there. Watch that video for Wednesday. Do the notes by tomorrow night. Let me know if you have any trouble uploading them or anything. And we might do some lab explorations on Wednesday. So awesome. And I have office hours, I think, right now, and then later this afternoon also, and tomorrow afternoon. Yeah, take care.